We can now close the parameter file and get back to the workflow. So next section of this workflow is a bias study. So it is very common if you have two different data sources of two different data types, or historic data and new data, whatever the two data sets are, it's very common to perform a bias analysis between the two so that you can evaluate if there is any bias. We typically perform this bias analysis by pairing the two data sets. And in order to pair the data sets, we need to specify a search. So to specify a search in RMSP, you need to use rmsp.Search. And if I look inside with Shift tab, we can see the arguments. We need to specify the angles and ranges, minimum number of composites, maximum number of composites, maximum composites per joule hole ID, and maximum composites per octant. So these are the typical arguments that goes into the search. We don't need all of these for a pairing analysis. In our case, it's isotropic search, so we are not gonna worry about angles. We are only worried about how far we go when we are pairing the data. In this case, I'm selecting 10 meters in the 3 directions. And I'm just setting the minimum number of composites to 1 and maximum number of composites to 1, because I really only care about the first point that I find when I search from another data set in order to pair them. So we defined our search. We can run this cell, and now we can initialize the pairing analysis class. So that's named rmsp.pair. The first 4 arguments are defining the data sets that we are using and the column names. So the first data set is the exploration data set with the gold column. The second data set is the blast hole data set, also with the gold column. The next argument here is our search that we have specified above. So this search is going to be used for some of the results. And also on top of that search, we can specify some multiple ranges that we want to test. So what we're doing here is we're using the numpy range function to generate a list starting from 10 up to 35, not inclusive of 35, with steps of 5. So if I run this, it generates a list starting from 10, then 15, 20, 25, and 30. And those are the ranges we are gonna test on top of the range that's being specified on our search. The next argument here are the prefixes, and this is just the name of each one of these data sets. So we have first the exploration data, and second the blast hole data. The next 2 arguments here are not very commonly used, but are available and are here for the demonstration. So these are lag distances that we can specify for the first data set, which is their exploration data, and for the second data set, which is the blast hole data. So in order to specify these lags, we use the rmsp.lags as the same class that we are going to be using for variography. Basically, the arguments here are spacing, tolerance, and number of lags. For this particular analysis, we only use 1 lag distance. And for the exploration data, we are using 50 meters with a tolerance of 25. And for the blast hole data, we are using 5 meters with a tolerance of 2.5. This lag distance is used to generate a H scatter plot. That's the same scatter plot that we could generate with variography that informs 1 experimental point on our variogram. So that's basically what it does. So let's take a look at the results. So after we initialize the class, we are showing the summary. So the summary is the pairs.summarize will show a summary of all the results. And let's take a look at what that is. So starting with the first plot, this is the scatter plot of the pairs that is found with the search of 10 meters, with a restriction of 10 meters. So for every blast hole location, we try to pair with the expiration data. So we look for the closest one. If the closest one is, say, 20 meters apart, that's above 10 meters, so that does not get used. So we go to the next blast hole data. If that blast hole data has a expiration data that is 5 meters apart, so that gets included in the analysis because it's below the threshold of 10 meters. So for all the pairings that were found, we build this scatter plot where we can check the correlation between the two data sets, and it also tells us what was the average distance of all the pairs. We are restricting this to a maximum of 10 meters distance between each pair, but overall we found pairs with an average distance of 4.17 meters. So the next result in here is coming from the H scatter plot for the first data set, which is the expiration. So that uses a 50 meter lag with 25 meter tolerance. The average distance of all the pairing that was happening was 54 meters. And just remember, the tail and the head of the pairing is in the same data set for the H scatter plots. So here we are looking at the expiration data separated by a lag of 50 meters. And this is the correlation. So basically at 50 meters, there's not much correlation left in the data. So, and the next result here is the H scatter plot for the second data set, which is H scatter plot for 5 meters with a tolerance of 2.5 meters. And that's using the blast hole data. So the average distance for this H scatter plot was 6 meters. And here we can see that there is a correlation at that lag distance. The next result in here is the CDFs of the pairs that were found for the blast hole data and expiration data. So just comparing the shape of the distribution of each one of the data sets. The next one is a QQ plot between the blast hole data and the expiration data. Is also a comparison between the distributions. The closest is from the 45-degree line, the closest the distributions are, and we can see where the deviations are. It's just a different way of looking at the differences between the two distributions. And lastly, here we have a table with the summary statistics of the pairs, and this table is generated also for the parameter defined in the search. So that's going to be a separation of 10 meters. For 10 meters, we found 615 pairs. The average within the expiration data was 0.71. The average in the blast hole data was 0.78. That gives us a 10% distance or difference. So that's kind of substantial. We can also look at standard deviation and the deviation between the two data sets, coefficient of variation, minimum, P10, P50, P90, and maximum. So that will give us a pretty good idea of how the statistics between the two data sets are deviating. Remember that we specified a test range. So in order to access some of the results for other ranges, what we can do is to run the pairs test plot. So if I run this cell, it's just going to show me this image with the x-axis being the search ranges, which matches what we have defined, 10, 15, 20, 25, and 30. The bars are the number of pairs that were found. So of course, if we restrict more, we find less pairs. If we allow for a larger search, then we find more pairs. What we're looking here is to restrict it the most we can while still having a decent amount of pairs for our statistics to be meaningful. On the y-axis here on the left side, we have the average difference between the averages or the means of the two data sets in relative terms, in percentage deviation. So we can see that for our selection, which was 10 meters, that's defined by the search that we specified. We had a deviation of 10.2%, which matches with the table that we had before. And we can see that as we increase the range, that deviation decreases. But for a pairing of 10 meters, we already have over 600 pairs. So I would say this is pretty stable statistics, and it's actually indicating that we have a high deviation.